All right, so the next topic is ideal gas law, and we actually cover several different gas laws in here. The ideal gas law is the only one that they actually put on your formula sheet. So you especially need to pay particular attention to this, but some of the other ones can come in handy as well. So that's what we're going to be spending some time on. We did talk in regular chemistry about Boyle's law. Boyle's law says that if we increase the pressure, the volume will decrease, and vice versa. So, so if you took a balloon, for example, and you squeeze the bottom of it and you decrease the volume, the pressure inside that balloon is going to increase. And so that's what we look at in terms of Boyle's law. And so you can probably think of other applications for that as well. So you can pause the video here and take a minute to see if you can solve these problems. All right, here is the work for that. So you can again pause the video and check your answers. All right, the next one is Charles's law, and this one deals with volume and temperature. Kind of quintessential example for this would be when you have a car tire in the winter time and you go out and you're like, oh, my air is low, and it's really just the temperature has gone down and the volume has decreased because of that. And then if you were to heat that up, by putting it on the road again, then typically the tire will inflate as the gas heats up due to friction with the road. So again, pause the video, see how you do with these. And here's the answers for these. Hopefully you were able to get that. Again, when you work with any of these gas laws, you have to make sure that your temperature is always converted into Kelvin before you can work with that. And then the magic conversion there is Celsius plus 273 will get you into Kelvin. So just keep that in mind. You always have to have your temperatures in Kelvin to make those work. All right, and then Avogadro's law deals with moles. And at a constant temperature, the volume is directly proportional to the number of moles present. And if you think about it, the moles of gas that are placed into a container, if the conditions of temperature and pressure are the same, then the gas can only occupy a certain volume. And if we know the volume and the number of moles, then we're able to figure out the pressure. And that's where we end up with some more math. So pause the video, see how you do on these. All right, here are the answers for these. So hopefully you were able to get those. And then Gay-Lussac is our next gas law, and he relates pressure and temperature. And you can pause and see if you can do these. Remember, your temperature has to be in Kelvin, so make sure that you make that switch. All right, here are the answers for those. And then they do some plotting of graphs with the ideal gas properties to help you illustrate those. And sometimes you'll see that, and then it gives you information about the absolute zero scale. Okay, so here's some plots with that. So you can see pressure and volume on here. Charles's law, you can see that as if they both increase at the same time or they both decrease at the same time. And then we can actually combine these gas laws together. So this is the combined gas law. Since the number of moles is going to be the same, oftentimes they will eliminate the moles out of here. And this is probably the combined gas law that you saw in chemistry. All right. So then that takes us into our discussion about the ideal gas law. With the ideal gas law, then we are working with pressure, volume, number of moles, And then an R, the R is a universal gas constant. This constant is given to you on your formula sheet. And then temperature, which again has to be in Kelvin. And if you're not sure what these other things have to be in, if you look at your R value, it tells you. So your volume would have to be in liters. To be able to use this number, your pressure would need to be in atmospheres. And then your temperature would need to be in Kelvin. So if you look at the R value, it's going to give you hints into what you need to have these in. And sometimes they will give you the volume in milliliters, and you need to be able to convert that into liters. So you'd have to divide by 1,000 to get that into liters. All right. So remember, if we were to take this and we were to try to manipulate it and get it into a density type formula, we could take out our volume and take out our mass, because that's what density is. So we're going to kind of rearrange that and manipulate it, and then you can get it into this format. All right. So pause the video, see how you do on these. All right, there's the answers. And then Dalton's law of partial pressure just says that if we have total pressure in a system is the sum of the pressures of the individual gases. And they want you here to calculate the number of moles that was N in the video, or I'm sorry, in the formula. That would be N that you're solving for. Here you've got your volume in liters. You've got your temperature in Celsius, but remember you must convert that into Kelvin, and then make sure that you're using an R value that deals with torr. And this is given that the vapor pressure of the water at this temperature is 20 torr. So you're going to have to subtract 20 from the total pressure before you get started. So Dalton's law of partial pressure says that the total is the pressure of the two gases, or however many gases it is, summed together. So if this is a part and this is the whole, to get the other part, you're going to need to subtract this off. And we'll be doing this in one of our labs where we're dealing with this partial pressure. All right, and then this one, we're dealing with pressure in kilopascals. And we have our container is a 1 liter carbon dioxide container. We have 300 kilopascals, and they're injected from that container into a new one. So we know no reaction between the two gases. What's the total pressure in the container? So pause the video, see how you do on these. All right, so here's the first one. Here we had the pressure of the hydrogen, and we solved that. We solve for our total hydrogen, and then when we got to the end, then we're subtracting out, we're able to get our moles of our hydrogen here. So that's where that 730 torr came from. That's what we were talking about before, because we were dealing with the 750, but we subtracted out the 20 for the water. So that's where that came from. And then here was our second question. This was essentially just a Boyle's Law question. But we needed to do it for the carbon monoxide and then one for the carbon dioxide. Once we got those pressures, then we had to combine them to get a total. So we're using that Dalton's law of partial pressure again. Then Henry's law says that we have a solution in a closed container. We have high pressure, more gas particles strike the surface of the solution and enter the solvent, meaning the concentration of the gas dissolved is getting greater. Gas solubility then is usually decreased when we increase the temperature. So if you think about like pop, for example, pop is going to hold its fizz much better when you have it cold. So that's why a lot of people like to drink cold pop, because it retains more of that carbon dioxide in there. And then if you relieve that pressure, that the gas will come out of solution. Popping your knuckles, for example, you've got fluid in your joints. And what you're doing when you pop your joints is you're increasing that space between the joints. So you're relieving some of that pressure that the gas that's in your joint comes out, and that's what you hear is the pop noise when you pop your knuckles. So that's just Henry's law, kind of a couple practical things that you've seen with Henry's law. So that takes us to the end of our gas laws.